Before Earth had oceans, continents, or even a surface, it existed only as ingredients. Gravity assembled the young planet through collisions. Rock striking rock, again and again. Impacts, compression, and radioactive heat helped turn the growing Earth into an intensely hot world. No forests, no animals, no breathable oxygen-rich atmosphere. This hostile world was Earth. But Earth could not remain molten forever. Its outer layers gradually lost heat and solidified.
As temperatures fell, water vapor in the atmosphere could increasingly condense into clouds and rain.
Rain struck volcanic rock, evaporated, fell again, and gradually collected across the cooling surface. Eventually, liquid water could persist at the surface, and Earth's story changed completely. Oceans transformed the surface, moving heat, reshaping rock, and creating an entirely new planetary environment. Water had arrived, but Earth remained restless, volcanic, storm-driven, and constantly rebuilding its surface. For billions of years, rock, water, atmosphere, and eventually life kept transforming the same planet. A molten, hostile world became this. The question is not what Earth is, but how it stayed possible. Almost every ecosystem on Earth's surface ultimately depends on energy arriving from one star.
Distance matters. Move a planet closer to its star and, all else equal, it receives more energy.
With enough absorbed energy, maintaining stable liquid water at the surface becomes increasingly difficult. Farther away, less stellar energy can make persistent surface liquid water much harder to sustain. Between those extremes lies a range where suitable atmospheres can allow liquid surface water. On Earth, pressure and temperature allow water to cycle through ice, liquid, and vapor. So was Earth's location the answer? Not quite. The sun itself has changed. Early in Earth's history, the sun was significantly less luminous than it is today. Yet geological evidence tells us liquid water existed early. So why wasn't the young Earth frozen?
The atmosphere changes the equation. Greenhouse gases absorb and re-emit infrared radiation, warming the surface.
But Earth's atmosphere was never fixed. Volcanoes, oceans, rocks, and later life kept changing its composition. Orbit helped make water possible. Keeping conditions suitable required the atmosphere, ocean, and rock to respond together. Rain does more than move water. As it interacts with air and rock, chemistry begins changing the surface. Carbon dioxide dissolved in water can react with silicate minerals, gradually transforming rock through chemical weathering. Rivers carry dissolved products of weathering from exposed continents and volcanic terrain toward the oceans.
The oceans became enormous chemical reservoirs, exchanging carbon with the atmosphere, rocks, and eventually life.
Over geological time, some carbon becomes stored in sediments and rocks, removing it from the atmosphere-ocean system. But Earth's surface is mobile. At some boundaries, oceanic material descends back into the planet. Geological recycling eventually returns some carbon toward the surface, including through volcanic degassing. Over immense timescales, weathering and carbon cycling can provide feedback that influences atmospheric carbon dioxide and climate. This recycling depends on a restless planet. So what keeps enormous pieces of Earth's surface moving? The mantle is mostly solid rock, yet over geological time, it deforms and flows. Earth still carries heat from its formation, while radioactive decay continues adding energy within the planet. Billions of years later, Earth is still cooling, and that internal engine does more than move continents. Beneath the slowly moving mantle lies something different, an enormous outer core of liquid metal. Motion within this electrically conducting fluid helps sustain a planetary dynamo and Earth's magnetic field. That field extends far beyond the surface, creating an enormous magnetic environment around the planet.
The Sun continuously sends charged particles and magnetic fields outward through the solar wind.
Earth's magnetic field reshapes that flow, producing a complex interaction between our planet and the Sun.
Some energetic particles reach the upper atmosphere, where their interactions help produce the light of auroras. But Earth's evolution was never Earth's alone. Beside it grew an unusually large planetary companion. The leading model begins with a colossal impact, ejecting material that ultimately contributed to forming the Moon. From orbiting debris, the Moon formed. Much closer to Earth than the Moon we see today. A closer Moon produced stronger tidal forcing, repeatedly moving enormous volumes of water across Earth's coasts. Over immense time, tidal interactions slowed Earth's rotation and pushed the Moon gradually farther away. As tides advanced and retreated, water repeatedly met minerals, energy, and changing chemical environments. Earth now had water, minerals, carbon chemistry, energy, and billions of years for reactions to unfold. Carbon can form extraordinarily varied molecules, providing chemistry with a vast vocabulary of possible structures. Sunlight, geothermal heat, and chemical gradients supplied energy that could drive reactions away from equilibrium. But complex molecules are not alive. Ingredients alone do not explain how biology began. Some molecules can spontaneously form boundaries, creating tiny compartments with an inside and an outside. Life also requires ways for molecular structure to influence what gets built next. We still do not know exactly where, when, or through which pathway the first life emerged. At some point, chemical systems acquired inheritance with variation, allowing successful patterns to persist differently from others. Once heritable variants reproduced differently, natural selection could begin shaping populations across generations. However it happened, by very early in Earth's history, life had become part of the planet. Some microbes evolved photosynthesis, capturing sunlight and transforming the chemistry of their surroundings. Life had adapted to Earth. Now, for the first time, life began rewriting the planet itself. For early photosynthetic microbes, oxygen was not the goal. It was a chemical byproduct. Much of that oxygen reacted before reaching the atmosphere, including with dissolved iron in ancient oceans. The reaction left a geological record, vast iron-rich layers, preserving evidence of Earth's changing chemistry. Eventually, oxygen began accumulating more substantially in the atmosphere, permanently altering Earth's surface chemistry. For organisms adapted to oxygen-free environments, this reactive gas could be dangerous, even toxic. This long transformation is associated with the Great Oxidation Event, one of Earth's major planetary transitions. Later, organisms using oxygen for respiration could extract far more usable energy from many organic fuels.
Atmospheric oxygen also enabled an ozone layer that absorbs much of the sun's biologically damaging ultraviolet radiation.
Over immense time, changing chemistry, ecology, and evolution opened opportunities for increasingly complex forms of life.
Yet Earth's climate remained capable of enormous swings, including episodes of near-global glaciation. Volcanism, climate upheaval, impacts, and extinction repeatedly transformed the environments life depended upon. Then life joined the system, altering atmosphere, oceans, soils, chemistry, and eventually the planet's appearance.
Look at Earth today, and the result can seem almost impossibly fortunate. A long-lived star, a favorable orbit, liquid water, an atmosphere, and a large companion nearby.
Beneath the surface, internal heat drives a restless planet, whose systems have operated for billions of years. Atmosphere, ocean, rock, climate, and geology were never separate stories. Each continuously influenced the others. Species vanished, environments changed, yet life persisted, adapted, and continued changing the planet in return. Seen only from the present, the pieces can look almost perfectly arranged for life. But Earth was never a finished paradise. For much of its history, our world would have been lethal to us. Climate shifted, ice advanced, volcanoes erupted, impacts struck, entire ecosystems disappeared. Life did not begin adapted to modern Earth. Evolution continually shaped organisms within whatever environments existed. But the relationship ran both ways. Living organisms repeatedly altered the environments that later generations inherited. Perhaps the mystery is not why Earth perfectly fits life, but how life persisted while Earth kept changing. Earth shaped life. Life reshaped Earth. For billions of years, neither story has existed without the other.